Welcome back, everyone, to another explainer. I am absolutely thrilled to have you here today because, honestly, we're looking at something truly spectacular. We are unpacking what is essentially a massive astronomical hit and run. Picture this. Our scene is a giant cloud of gas and dust. Our prime suspect is a rogue, high-speed star. And the crucial evidence? Well, it's hidden deep within infrared and ultraviolet wavelengths. We're going to decode the forensic data gathered by some of our most powerful space telescopes to figure out exactly what happens when immense cosmic forces violently collide. Okay, let's dive into this. This breathtaking expanse is Caldwell 31. You might also know it as IC 405, or my personal favorite, the Flaming Star Nebula. It's a massive emission and reflection nebula located right within the Aurigae constellation. Now, just to ground us in our cosmic neighborhood for a second, this nebula sits about 450 parsecs away. To put that into perspective, that translates to roughly 1,500 light-years from Earth. Now, to the naked eye, or, even through a standard optical telescope, it looks incredibly peaceful. Just this gorgeous, ethereal structure of gas glowing softly in the dark. But, as we know, looks can be incredibly deceiving. This region of space is actually the site of an incredibly violent, ongoing interaction. To really understand the absolute chaos happening inside Caldwell 31, we need to introduce our main suspect. We're dealing with what's called a runaway star. Basically, this is a high-velocity star moving abnormally fast through the interstellar medium, usually because it got violently kicked out of the star cluster where it originally formed. Our specific culprit in this hit-and-run is a runaway 09.5 V-class star named HD 34078, also known as AE Aurigae. This bright, dominant star is currently crashing headlong right through the otherwise quiet gas and dust of Caldwell 31. Make no mistake, it does not belong here. It is a very fast, very destructive intruder that's just plowing through. So you're probably wondering, how did this star end up trespassing in Caldwell 31 in the first place? Well, if we trace its dramatic, violent history, the story begins roughly 2.5 million years ago. Back then, HD 34078 was hanging out far away in the Orion star-forming region, but it got caught up in a massive binary interaction. Think of it as a gravitational wrestling match between multiple high-mass star systems. The result? Our star was completely ejected, just sent hurtling through space. Fast forward to the present day, and it's blazing across the sky on a high-speed collision course with Caldwell 31, literally tearing through the cosmos with a staggering transverse velocity of about 40 milli-arcseconds per year. The sheer amount of kinetic energy involved in this encounter is absolutely mind-blowing. Now, when a massive object like our runaway star plows into a dense cloud of material, it definitely doesn't slip through quietly. It creates a massive BOWSHOCK. Think of a speedboat racing across a totally calm lake, pushing this enormous wake of water ahead and out to the sides. Or imagine a bullet passing rapidly through the air in slow motion. The star is acting exactly like that speedboat. It is physically compressing and intensely heating the gas and dust of Caldwell 31 as it violently forces its way through the nebula. Now, what's really interesting about all this is that this dramatic collision, it's completely invisible to our standard optical telescopes. To act as cosmic detectives, astronomers had to pivot and turn to the SPITZER space telescope. By shifting our view into specific infrared bands, specifically 8.0 and 24 micrometers, SPITZER acts as our forensic evidence. It suddenly reveals the hidden arc-shaped BOWSHOCK. You finally get a clear, distinct view of that bullet-tip interaction region, along with the incredibly complex, clumpy dust features being forcefully shoved out of the way by the star's immense momentum. The physical impact of this collision becomes entirely undeniable once we start looking at the thermal data. There is a stark, fascinating temperature contrast here. The ambient background dust of the nebula sits at a fairly chilly 60 Kelvin. But when we measure the dust directly in the shock region, which we derive from the ratio of 24 to 70 micrometer emissions, the temperature spikes to over 90 Kelvin. And this brilliantly illustrates the sheer physical friction occurring in real time. The kinetic energy of the star's movement is literally transferring into the dust, heating it up precisely at the point of impact. But hey, 90 Kelvin is just the start of the thermal extremes. When astronomers use the SPITZER Space Telescope to look at the pure rotational emission lines of molecular hydrogen in these bright nebular filaments, they found an average temperature of an incredible 400 Kelvin. This massive leap in heat isn't just from physical friction anymore. It's being driven by intense, non-uniform excitation. Basically, the runaway star, HG 34078, is blasting the surrounding gas with a relentless, brutal ultraviolet radiation field. So the star is both physically plowing through the gas and actively cooking it with UV photons at the exact same time. It's a double whammy.
And that intense radiation leads us right into the central mystery of our explainer. When researchers used a rocket-borne long-slit spectrograph along with the Far Ultraviolet Spectroscopic Explorer, or FUSE, they fully expected to see a fairly predictable decay in light. Instead, they found something bizarre. As they measured further and further into the blue end of the far ultraviolet spectrum, the ratio of the nebula's surface brightness compared to the star's flux suddenly skyrocketed by approximately 2 orders of magnitude. That is a massive, entirely unexpected spike in blue light. So the big question that completely baffled astronomers was, what exactly is causing this extreme far UV blue rise?
To crack this case, the research team laid out 3 primary suspects to explain this totally bizarre blue dust phenomenon. Suspect number 1. Was it differential extinction? Meaning, was the light from the dominant star, HD 304078, simply being blocked and filtered in a very specific, weird way by the foreground material? Suspect number 2. Could the dust grains inside Caldwell 31 possess highly unusual, abnormal physical properties, causing them to scatter light entirely differently than typical interstellar dust? Or, suspect number 3, was this mysterious blue light actually an emission coming directly from the nebular dust itself? Well, after some rigorous testing, standard scattering models that used simple, uniform dust geometries completely failed to reproduce the spike in brightness. And while the FUSE data did detect a really rich spectrum of fluorescent molecular hydrogen, researchers determined that actually wasn't the dominant cause of the blue rise either. So the crucial takeaway here is this. The culprit isn't some single exotic particle. It is the extreme, highly complex clumping of the dust combined with the highly irregular geometry of the interstellar medium itself. The nebula is so intensely clumpy and uneven that it scatters the far ultraviolet light in chaotic, highly localized ways. Simple, uniform models just can't account for that level of messiness. Which brings us to a really fascinating, profound thought to end on today. We know this complex, clumpy scattering is happening because we have the instruments to observe Caldwell 31 up close, just 1,500 light-years away, right in our own galactic backyard. But what if we didn't? What if we observed this exact same event from deep space, lacking the resolution to zoom in, say with a spatial resolution of less than 0.4 parsecs? Well, all this chaotic scattering and that blue rise would just blur together. To a distant observer, the system would falsely appear to have a stellar continuum that was significantly less extinguished by dust than it actually is. Ironically, this is the exact same optical illusion we see when looking at distant starburst galaxies. It is a powerful reminder of exactly why detailed, high-resolution explainers of our own cosmic neighborhood are absolutely essential. They give us the critical Rosetta Stone we need to accurately decode the mysteries of the deep, distant universe. Thank you so much for diving into this astronomical mystery with me today. Keep your curiosity sharp, and I'll see you in the next explainer.